Hi, everyone. Welcome to discussion number 3 for data structures and algorithms. Lilia, I'm in that class too, so I know what you're talking about. Yeah. Um, but yeah, we start every morning off, every time I lead a discussion with music. And if you have suggestions for songs to play, feel free to write them down. I was actually thinking about making a Slack channel / group for this discussion. The only issue I have is that I don't know how many of you guys show up to my discussions and how many go to Kevin's. So I don't know how we're gonna do that yet. But if you like that suggestion, feel free to voice your opinion and we'll discuss it in a little bit more detail. And we can use that Slack channel to then modify the playlist that I have in place. Additionally, because I believe you guys still haven't gone over stacks and queues in class, we're gonna have an interesting discussion where I actually try to refresh you on that a little bit, not go into too much detail because that's what Professor Aman is gonna go over. But yeah, it's gonna be interesting, and we'll see how that goes. If you have any questions, as usual, feel free to interrupt me and ask. I'm gonna start sharing my screen and start the presentation now. Do we have any other questions before I begin? I guess not. I don't want you guys seeing this screen. I want this, yeah. Okay. Set up chat. Okay. So as I said, we're going over stacks, queues, and lists. We're gonna start off with stacks and queues, and we're gonna look at a problem related to those two. Then we're gonna go into linked lists and talk about a method of iteration through linked lists, and then we're gonna do debugging. I'm gonna kind of speed through the rest and focus on debugging because we actually have a participation activity and we're gonna do some live coding. So stacks, do any of you, you must be familiar with stacks, at least a little bit. I know that Mr. Fox used to go over them in programming too. I don't know if they still do that. But can anyone tell me like one property of stacks that you know of? Yep. Yeah. That's yeah. Those are great answers. Yep. That's the main defining property of stacks. So first off, stacks are an abstract data type, which means that the implementations vary and you can use different, how would I say that? You can use different actual like data types like arrays and linked lists to implement a stack. You're not limited to just one functional implementation. And those can vary across programming languages depending on, yeah, Lily, thank you. Those can vary across programming languages depending on what the language allows itself. The most common implementations that we have right now are linked lists and arrays. As you guys said, stacks are first in, last out, or last in, first out. And you can just think about like dishes or stacks of rocks or whatever, stacks of pancakes if you want. You put something on top, you have to get it off the top first. It's kind of tedious to get it off the bottom. And usually that's what we use them for when we need that top access from the last thing that we entered. Do you know any of the common stack operations? So what can we do with stacks? Common names for functions in stacks. Nice. Push, I have that one already. Yep, peek, good job. Pop. Peek is sometimes also known as top, which is just depends on how you implement it. And the last one is empty, which is usually just to check if the stack is empty. Some applications of stacks. We're going to look at depth first search algorithm. I don't know how familiar you are with these, but those are the yeah, Lily, that's a good one too. Erase, where you just clear it all. Um, depth first search algorithm is an algorithm in which you go to the deepest point of your data structure and then start checking from there. So suppose you have a tree or a linked list, you would go to the last node of that linked list, iterate through it, and then check if the last element is the one you're looking for. If it's not, you pop it, check the next one, you pop it, etc. Reversal algorithms, we're going to look at these. If you want to reverse a string, you keep adding characters one by one into a stack, and then you pop them out and add them to a new string, and then you'll get the string backwards. Those, yeah, so function and method calls on the stack is just how memory is organized, because every time you call a function, you go into a function, it's added on top of a stack in the memory, and it's going to operate within that one until it either opens a new function or it's done with that function and it pops it out and then goes back to the next one. Expression evaluations, so those are usually for close checking if the parentheses are closed, and we're going to look at that example in detail. And backtracking, it's fairly simple, as well as syntax parsing. Queues, common operations in queues. I mean, we have a picture already, so I don't know if you guys want to talk about or suggest common operations in queues, or are you good to move on? Okay, so queue. Can you tell me what the difference between a stack and a queue is, though? I didn't cover linked lists. Good job, Liam. So it's, yeah, first in, first out. That means, yeah, think about a buffet line or any line you're if you're waiting. Well, we call them queues, funnily enough, right? But the first person to get in line is the first person to get out of it. Seems the most fair approach, right? No cutting is allowed, obviously. And then we have some operations. We have enqueue. It's triggering, but in C++, it's called push. You're just gonna have to deal with it, unfortunately. Dequeue, once again, C++ uses pop. And then you have front and empty. Front is similar to stack's top. You check the element that's gonna be removed from the queue to see if it's there or to see what it is. And then I don't know if Lily, if there's a programming language that actually uses enqueue and dequeue. I just know that conceptually when you talk about queues, those are the like terms you use for those functions. I don't know if they actually have specific languages that legit do use these words. So notable applications of queues, breadth first search algorithm. As opposed to depth first, you don't go to the last node, you add them all and then you check from the first node that you added to see how far, like what the breadth of your search is going to be. So like how far you have to go until you find the right element. Scheduling algorithms, same thing as the buffet line we talked about. Handling interruptions in real-time systems. So if you have like if you have several processes going on. Oh, Adam, Python uses enqueue and dequeue. I didn't know that. I don't really use Python. I have a beef with Python, but that's good to know. That's one plus it has actually in my books. But if you have processes on your machine that are running and Python is cringe, yeah, it is, Jaden. I agree. Those processes, if they're interrupted, they're going to be interrupted in like the queue basis. So they're going to stop working based on the first one that started. And now we have a poll. I actually have a Mentimeter for you guys, but first I want to ask you what questions you have for me at this point. Any questions? And you can ask questions while I set up Menti. No questions? We all good? I think they are. As far as I know, I think they are. And that's usually what we're going to be talking about. These questions that I'm going to ask you in this poll, they are going to assume that you're using a linked list to implement them. You guys can now see the Menti code too. Do you guys need me to write down the Menti code in the chat, or are you good? Let's see what Menti can do for me. I'm not gonna start the question yet. I'm just gonna see how many of you guys are here. This is gonna be easier. There's about 35 of us in the meeting and only 23 people joined the Menti, and yeah, it is. I will open it for you guys in at 11:30 or 11:15. Sorry, it's gonna be due at 11:30. Okay, I'm gonna start the questions now. Are we all good? Anyone scream at me in the chat if you want me to not start the question right now. Otherwise, come on. Okay. First question. What is the time complexity of a push and queue operation for stacks and queues? And that's assuming that we're building them as linked lists. Yay, you guys are so good. Well, we had a split here, but that's okay. So the thing is with stacks and queues, you usually have, especially when with linked lists, but you usually have a pointer that points to the element that's going to be removed next. So you already have that element saved, and all you have to do is access it and remove it from memory. So all of those operations are going to be O of 1, making the total complexity of push and enqueue O of 1. Next one, how do I go? Okay. Oh, we have the Android is quite possibly my favorite one. Okay. Good job, guys. Next one. What is the time complexity of pop/dequeue operation for stacks and queues? Which I just talked about essentially. Because yeah, we're doing better. Same thing. If you want to add or remove, it doesn't matter because you always have that one reference to the last element. So you don't have to iterate through the entire stack or queue to add elements. Oh, I skipped the leaderboard. Wait. I like the drama of swapping places in Menti. That's my favorite part. And last question is, what is the time complexity of top front peak operation for stacks and queues? And that is going to be one. Yay! Good job, guys. Let's see. Slay, yeah. Oh, oh, oh my God. That was so dramatic. That was like the last moment. Yeah. Oh, Ricardo, I don't think I would recover from this one. Okay, guys, we're gonna go back to the presentation. And you better get your revenge. Okay. Starting the presentation. I still don't want you guys to be seeing this one. I don't know why it does this. There we go. So we're done with the poll. Do you have any last questions before I move on? Last questions, final questions. No more questions after. Okay, so we're gonna look at an example, which is, I talked about it already, but this is like checking if you're closing the parentheses you open in your strings, and an input string is valid if the open brackets are closed by the same type of brackets. So if you open the parentheses, you have to close them, and you have to have an even number of those. They have to be closed in the correct order. So if you open the curly brace, you have to close the curly brace. You cannot close it with a square bracket. And every closed bracket has a corresponding open bracket of the same type. You guys have any suggestions how we would go about this? I'm willing to look at both brute force approaches and stacks and queue approaches. Any suggestions? This might be a little long to type in the chat, so I'm just not gonna wait too long. Well, it is gonna be a stack and a queue. If um, I actually do we use queue? Let me see. No, we use a stack. You're right. But the way you do it is you have a stack of characters. Yep, good job. You have a stack. Every time you open a parentheses, you push it onto a stack. If it's not an opening, or if it's not one of the opening parentheses, then you have four cases basically. If the stack is empty and a closing parentheses appears, that means you have an invalid string and you return false. If the character you're trying to add to the or the character you're examining is a closing, I don't know what this one is called. Is this one parentheses? These are they have confusing names. But the top is not the opening match of it. You return a false because that's not what we're looking for. It has to have a match. If it is a match, you pop it. If if the character you're examining is a closing curly brace and the top is not a curly brace, you return false. Otherwise, you're going to pop it again. And if the character you're examining is a square bracket and the top is not a square bracket, you return false. And then ultimately, after you're done looping through the entire string, you return the result of checking if your stack is empty. So in a case where you added a added an opening parentheses, any of these, but there were no more characters following, you would get a false here, and then the function will return false again, which is what we're looking for. Practice for stacks and queues. There are some lead code problems, and you can look at these once we publish these slides. Lead code is great. I don't know if you guys already used it, but it's very, very useful for preparing for technical interviews, which we'll talk about in some other discussion after we establish when we're going to do a mock interview for you guys. Linked lists. Finally, I think you guys went over this in class. So this shouldn't be much of an issue. We all know what linked lists are. They have nodes, and those nodes are linked by pointers pointing from one node to the node that follows the next one. We can have a singly linked list where each individual node has only access to the node that follows it in one direction. So either the one that comes after it or the one that comes before it. Or you have a doubly linked list, which has pointers to both the one that comes after it and the one that comes before it. We good on that one? Oh, you can also have like a circular list where the last node points to the first node of your list, in which case you just have a interesting graph. So reversing, we're going to talk about this problem for the rest of the discussion, which I'm not honestly gonna go into in detail because I also have to open the quiz for you guys. But if we have, we can use a stack recursively or iteratively to reverse to swap the places or order of pointers, I guess. Just remember that all algorithms that you create, you can either go, oh well, if you need some iteration, especially with linked um, data structures, if you do them iteratively, you can also do them recursively and vice versa. So whichever one you're more comfortable with, feel free to use it. And we have like a helper function here that shows in let me draw on it. Okay. A helper function here that would actually reverse the nodes. You this one does it recursively. So if the current node is null, you return the previous node, which you pass into the function. And that's gonna happen the first time you access the. Yeah, if you have a doubly linked list, you don't need to. This is just for a singly linked list. And then you call a reverse helper on a new node. I assume that you create because it's a pseudocode. But the reverse helper is going to take the current node and the one that follows it. So what's it going to do next is it's going to take the next and assign it the previous one, essentially swap them and return this one, which is a little like it's funky. I don't have too much time to go over this, unfortunately. But the primary function calls for a helper function and sends previous as null because we don't have any previous nodes at the head of the linked list. Helper function takes in a previous and a current node to reverse their connection, so it swaps them essentially. In the it has obviously the base case, which you need for all recursive functions. So if null, return, just return, and recursive call, which happens here, and then obviously the step of swapping them and returning. Why are we still talking about this? Oh yeah, so it's going to be obviously O(n) of space and time complexity because you have to iterate through the entire linked list, reverse all the connections. When you call recursion, a lot of times it's gonna, a lot of times it depends on how you pass nodes, but because we're not passing them by reference here, it's just gonna keep creating new ones and replacing the old ones. So every time you create a new one, you allocate a separate space in memory, which is why the space complexity is O(n). And this is just details and process of how it happens. Returns all of these after your current node is null. So after you're, well, when you're at the end of the list, and then you keep just swapping them. Technique of iterating through linked lists that we're going to talk about right now is called the slow pointer fast pointer, which is basically like it's also known as the runner technique, but it's you have two pointers that run through your array. I'm gonna clear. Where's clear? Clear all drops. There we go. You have a slow pointer and a fast pointer that both iterate through your entire array. It's just that the fast pointer is gonna move well, obviously twice as fast as the slow one. So or however many times as fast as the slow one. The way you can do it, usually what we do is you would have a Boolean, and every time the Boolean is true, you move the slow pointer. Fast pointer moves every single time, but every time you move the slow pointer, you swap the Boolean's value to an opposite, so you negate it, and that way you have the speed at which the slow pointer moves. And I'm pretty sure that we're going to talk about that, but obviously one is fast, one is slow. And yeah, this is the example I was talking about. This way you would actually only iterate through, suppose that you have to find a half, like the center of your linked list. You would only have to iterate once through your linked list this way instead of having to do it twice, which speeds up your algorithm. Especially, yeah, you could do that too, Nicole. Yeah, that one works too. And if you want to do it every, like, I don't know, fourth step of the fast pointer, you can do it with mod 4, etc. Yeah, and this is especially helpful when you do not know the length of a linked list. Sometimes you want to find out, sometimes you don't. I need to again. Applying slow pointer, fast pointer. So yeah, if you want to remove the nth node from the linked list, it could, yeah, you could do that too, Sai. You could move the fast pointer twice. Um, you could. It doesn't, whatever makes you understand it better, whatever works for you, that's fine too. So suppose that you want to remove the nth node from the end of the list and then return its head. Know that the nth node always exists. I guess N1 represents the last node in the list because you count obviously from the end. And if N is 2, that would be, you want to remove 4, I guess. Yeah, you want to remove 4. The way you would do it is, I guess they don't tell you that, but you could create a space of 2 between your slow and fast pointer, and then once the fast pointer is at the end, you remove the slow pointer, if that makes sense. Just remember that this is not the only way to solve problems like this. Um it's just more efficient, I guess. It iterates through the linked list once instead of doing it several times. Also note that this is not a silver bullet. It's not going to work in all problems. And you need to think about when you want to apply. Yeah, you check essentially, you once you hit the end, your fast pointer is going to be null. So you are actually looking for that null pointer. Um, you're waiting for that one, and that triggers the action for the slow pointer. Yeah, this is the example of the code, which I am so not gonna go into detail because I already did it for you guys. Yeah, once you hit the null pointer with either of those, looping twice, yeah, it depends on how large your depends on how large your linked list is. You might really not want to do 2 iterations of it. Yeah, you might jump over it if you're doing the fast pointer. Yeah, if you do it twice, if you move the slow point or the fast pointer, if you move the fast pointer just once, you will not have that issue. And this is the example. You can look at it. I'm just a little behind on time, but yeah, it's basically, I think this one uses the counting to create the distance that I talked about earlier already. So I'm just gonna skip through all of this because we have the quiz. Let's go. Why do we have so many slides?